exercise. And also, before doing the exercise, I'll go over the nuclear sim, and then we'll go over an exercise together after that. So the Petrophysical Calculator, this is you get to it from the same Earth model.
Remember to share your screen.
Oh, thanks. Okay. All right, is that showing?
Yeah, and do you want us to start from a new well, or doesn't matter?
It doesn't matter, I don't think. I mean, for the exercise, probably we'll make a new well, but this is just for the to show stuff. So I'll just leave the one that I have open. I was just playing with some stuff. I have a couple. Yeah, so for the purposes of just showing the tools, the Petrophysical Calculator. So here we're in the Earth Model Builder, and the Earth Model Calculator you can get to from here. And we already mentioned that you have the calculate bulk properties when switching layers, and so you have these checks here. And whenever you make a change and you switch, well, it's actually when you switch layers. So making changes will change the Earth Model layer that you're changing. But then when you change layers, or when you click calculate, it will go in here and it'll look for all the boxes that you have checked, and it will run those items. And so each of these items then you can expand, and you have lots of options here. You know, so for instance, if you want to change between UT NuPro and SNUPAR, you can do that here. If you want to include salinity or not. And similarly, a couple of these have larger controls elsewhere. And so, for instance, effective medium theory. If you click that, then that brings you up to this, which we saw before. And likewise for the NMR, if you click that, it'll bring the NMR Studio, because these are quite elaborate ones, but we still wanted to have the ability to see them in here, because they are Earth model calculations, basically. And then over here we have some that you may be more used to. One of them, you can calculate the water resistivity. So if you've already set up and usually they say what they depend on. So if you've already calculated if you already put in say the salinity and the temperature, then you can get water resistivity. Or you have the option of calculating either of the other three. So you can just kind of, depending what data you have, you can calculate the others. Similar with Archie's. And you'll see, so basically a lot of this stuff I'm going to be using tomorrow for the NMR exercise. So really, the nice thing about the use case exercise is that it really shows you how to put the things together in order and build up an Earth model in order to try to match your logs. But in this case, I'm just showing you where it is. And some of these we used in the exercise in a few minutes. So here you have the options of, you can go back and forth between resistivity from water saturation or water saturation from resistivity, again, depending what you have. A lot of times you import resistivity from logs, and then you want to see what water saturation you calculate from that. And you notice here we have several of these have buttons that go to rock classes, and that's if it's related to rock classes. This allows you to look at what rock classes you have and what the settings are. And so, for instance, for Archie's or other types of Archie-like equations, this is where you set the parameters, and so you can quickly get to it. Same thing with the Teamer model. And we already showed you that you have that in the rock class as well, and you have the options to calculate it different ways. Check these, and the temperature, it just allow you to set a gradient. So usually you have a sort of a fixed temperature by default, but if you want to actually make a more realistic temperature gradient over some distance, then you can set the endpoints, and it'll just give you a linear gradient there. And then the overburden pressure, that calculates, that starts at the top of the well, and it takes whatever your bulk density is from the top of the well. And then uses the total bulk density to calculate the pressure at a given level. And yeah, now obviously the more accurate pressure is what you've measured at different places, which is probably what you use in the pore pressure. But this, if you're just setting up a demo well or something, this can give you a starting point to get an idea at based on your material, what pressure you might roughly expect. And then finally, we have pore pressure. And this one is something that we just added this year. And it makes it easier to create say some synthetic model or something, which we used to be able to, we had always had the capability to initiate your fluid flow simulations with this type of calculation, but now we've added it just to the basic Petrophysical Calculator. And so the options that you have here are you can calculate just based on the current saturation or the current fluid that you have, and you give it a start, like basically it defaults to the modeling interval, but you give it an interval, and it will then calculate across that interval based on the fluids what the pressure should be given the reference pressure. And then you also have the option to include water saturation. And what that means is instead of just taking into account the current saturation or the current fluids, you give it a free water level, and based on the free water level below that, it'll set it to 100%, and then above that, it'll use the PCKR curves, and that's why we have the rock class set here. So you can go to the rock class, and then it goes directly to PCKR curves, because these are what's relevant for calculating the water saturation. And so basically then you can set your distance here. So right now, let's see, we'll make this like 3,800 to 4,000. Oh. RMB must be 1,000 feet. It's weird because it worked. It's running. Okay. I didn't hit calculate. So, okay. So I'll have to check that. But generally, you can set the values here, and then you click water saturation, set your free water level. In this case, you can see where I set it at 3,900. Oh, I think I have the wrong well here. Let's see. I had two wells open. I was using the wrong well. Okay. So here I had set to 3,900. I said include water saturation. And so then here you can see where it set the water saturation to be 100% below the free water level, and then use the PCKR curve to calculate the increase or the decrease down to 0 in the oil layers. And then over here, it calculated the pore pressure based upon the free water pressure. And notice that, I mean, this is an Earth model calculation, so it's calculating by layer, and that's why you see these blocky steps here. Because if you want there to be more higher resolution, then you can either put in your own fluid boundaries, or you can indicate a higher number here. So you have basically an option of any number that you want. Okay, and then of course you can select where you want everything to be calculated. you have the choice of all petrophysical layers. In this case, these are all fluid layers, so I only have one petrophysical layer. And this is related to what Joaquin was talking about earlier, the difference between petrophysical layers and fluid layers, because this is changing the water saturation. We don't want to change, if you set petrophysical layers relating to the type of rock or the porosity or something like that, we don't want to affect those. So we're just putting this in to allow high resolution variation of water saturation. And then, so we have similar in the log calculators. We have a log studio, and there's, oops, this one doesn't have any logs. Okay, and this one. So in the log studio, we have different types, different calculations here. You can also do the Archies, but in this case, typically you're going to set logs that you're going to operate from. And so you still have the ability to calculate pressure, temperature, water resistivity, permeability. And then you can also do some standard log calculations like density neutron averaging, or changing density, porosity, the bulk density, and matrix corrections and so forth. Now, just as an example, I'm going to show, in this case, I've imported a gamma ray log. And one very common thing that we do is take the gamma ray log and use that as an estimation of what your shale concentration is going to be. And so in this case, we select the linear and we look at the range that we have. And so this is 30, goes down to like 22. So we pick 20 and up to 130. And so we say that we want the, basically these determine where the 0 to 1 is going to be defined on the gamma ray. And because it's linear, it's just going to pick a proportional shale concentration proportional to the gamma ray. And then you pick the log. In this case, we only have one log set, and we're going to use the gamma ray. And it tells you what output log set. So we're going to put it back to the same log. And by default, it'll pick calc. And so if you do this more than once and you want to try it with different parameters, you can always set a different name in here. But you know, if we hit then calculate and then go to this log set, you see down at the bottom, you have the shale concentration. And then, so that's shown as a log here. And so you can then see the how that was generated in proportion to the gamma ray log. And then of course, I think what Keen has already showed you, that then you can take that and populate for instance, the Earth model properties, say the shale concentration in the Earth model with that calculated log. So that's sort of a workflow that we commonly use, and you'll see that tomorrow in the use case. So now,
hey Bruce, can I don't know how this value possible, but can I suggest something for this here? So when we try multiple things for calculating any of these curves, clearly it save it inside the log set. If we can add an option to display right away before saving, so we can see it, instead of every single trial will be saved and then we have to go and display it. So just something for the future, if we can have an option for display on the fly, and if we decide if we like it, then we can save.
I see. I think something that we can do that is in between is, if you save it with the same name, does it get updated, Bruce, right away?
Yeah, all the time. Yeah, I mean, I can change this to 150 and hit calculate, and you'll see this change. See that? It just updates right there, so you can just see right away the changes.
Yeah.
And if you don't like it, you can always just delete the log.
Yeah.
Um,
How does that sound to you, Hesham?
Yeah, it's you know, yeah, I'm trying. I'm kind of linked to the commercial software, something like TechLog. So it always give you the three options: display, display and save, or only display. So but by this way, it just will make our life easier and faster. But if it's hard to honor this in from the development side, I think this will solve the solution as well, serve the purpose.
I see. We'll put it in the list and see what can we do. If we think of a simple way to do it, which I think we can, and
I
we'll
mean,
include it. But
are you thinking of a full track, or just you want just to see the shape of it in a like
Yeah,
just
so it will generate a full track automatically displaying the property that you are calculating, and then if you like it, you keep playing with it until you find the best solution that you like, and then you save it.
I see. Yeah, I don't think that would be too complicated. Just to open an empty track display with the proposed calculation. Is that what you're thinking?
Right. Yeah.
Yeah. Thank you.
okay. So then I also want to show custom calculations. And so as you said here, you have the option of doing simple ones, like if you just want to add 2 logs. And then you can also do more complicated ones. And so this one, for instance, like one super simple thing that you might want to use this for is just to change units. I mean, maybe this is kind of ridiculous, but if you have like a calibration, which is in feet. Oh no, it's not feet. Data is in inches. And if we wanted to change that to feet for some reason, so we want to divide by 12, so we can just say, you know, I can just leave this, or I can put HCal feet. And then we'll say and then pick the units, feet. Oops. Okay, there we go. And then because we had the destination log sets, that example again, we'll see that this shows up at the bottom as feet. And so now we have a new one where we just change the units, but obviously you can put in here as complicated of a function with MATLAB functions as you want. And so we've used this for quite a number of different things. Like for instance, if you watch the NMR webinar that we did, we used this to calculate SDR from the NMR log outputs. Okay, and then we also have the depth shift. And so so for instance, in this case, if you look at these layers, you may find that you feel like here I've plotted the density and neutron porosity, and we have the gamma ray over here. And and you may feel that these are not lined up properly. Maybe you want these two boundaries to line up, and so or maybe you want them to line up with the gamma ray. Actually, we can. Oh, another thing, if you want to, for instance, move the gamma ray to, or copy the gamma ray to this thing, you can hit the control button and then move this over, and you just get another copy of the gamma ray over here. And so here we can see that, oh, maybe this thing is a little bit off, and so we want this this transition in the density to line up with this transition in the gamma ray to make them maybe somehow they were calculated a little bit off. So then what we can do is go over here and we'll select the gamma ray, and actually I think let's get rid of all these. Okay, and so then that's this thing here. So there's a number of ways you can add anchor points here by saying add anchor and type in a particular value. Or you can go up here and right click and put add anchor. And then what you can do is we might want to actually make this so that it's live. Well, so that all of them are live. But so this then you can see where this shows you the change from where it was to where the new one is going to be. And then when you hit apply, and so here, oh, I didn't hit apply. There we go. Okay, so then you can select as many, so this will create a shifted log set when you hit apply, and you can select as many of the logs to add to the shifted log set. So in this case, what I did is I said, okay, well, I think that I want the neutron to shift along with the density. Maybe they came from the same log set. And so then what you can see is then if we plot that shifted log set, then if we move this, we'll see that both of those get stretched by the same amount. And so this is how you can put as many of these anchors as you want, and you can do all the stretching and squeezing you want. And if you just want to shift an entire log set, you can do that just by putting one of these in. And so then it just shifts the whole log set. And anyway, so yeah, basically the anchor just anchors whatever you had to where it is. And so you can stretch by putting two anchors, or you can just shift the whole log set by just putting one anchor. Okay, so now let's see, that was that. Okay, so now I want to go into, before we get onto the to doing the exercise, I want to show you some new stuff that we added with the nuclear calculator or nuclear simulator. And so we've added some stuff to this. One of them is that now both the wireline and the LWD will show invasion effects. And if you come on Friday for the simulation, or I mean for the scripting exercises, we're going to do the last exercise is going to be one where you can actually use scripting to look at the depth of investigation of those two, both of these logs, and you can compare them because now you can, because both of them take into account invasion, you can compare those through a scripting exercise. And we also added this gamma ray consistency capability. And what this does is, as you guys probably know, you have the gamma ray. One of the ways of calculating gamma rays to take the concentrations of neutron, thorium, and potassium and add them in a linear fashion. And so the things that are actually stored in the Earth model of the uranium, thorium, potassium concentrations, and then gamma ray is a dependent property. However, as you can see from this, the gamma ray value is going to depend on these coefficients. And so you have several different options here. And if you select one of the custom options, so you can select, say a sim custom if you want this to be, 6 or something and 2.8, you can do that. And then you can, or you can do like the standard SGR option, or you can say whatever's in the Earth model. And then this shows you that what it had in the Earth model is the original wireline calibration that we had. And if you happen to select one of these, so for instance, if you say, well, I'm going to do the simulation on SGR, now the Earth model is still something different, right? Because if you check the Earth model, it has these values. But we can do a nuclear logging simulation using any of these for the gamma ray, and then for comparison purposes or something. Likewise, we can, if we want the Earth model to use one of these others as a calculation, you hit sync. And so now it synced the Earth model to these values. And so now if we change the sim to the original wireline sim calibration, and then go back to the Earth model, we see that it kept the values that we synced the Earth model to. And so in this way, it allows you to, it prevents this inconsistency between the Earth model and the simulations, unless you expressly desire that. Another thing that we added was this Earth model capability here. And so now if you set different borehole diameters in the Earth model, it will use those as opposed to the standard 8.5 or whatever custom value that you set here. And now we've did a few other things just in where things go. Move this to the left to make it more easier to use and less confusing by getting rid of some things that usually weren't relevant. And we also added this log suffix. And so this is nice. So if you want to, I mean, you can do something as simple as put, underscore 1A or something. So your first, or you can say, whatever, this will add a suffix to the log set that you generate. And the other thing that we have is this run nuclear calculation first. Now, as you know, or you may not know, I think a lot of people didn't know, this simulation depends upon, that's weird. The simulation depends upon the Earth model nuclear values, namely these uranium, potassium, and thorium, which are calculated when you run the nuclear calculation, this like SNUPAR or UTNUPRO that we talked about before. And so if you have this checked and then you run the simulation, it will automatically update those. So a window came up on mine, it was on a different window, but the window came up saying that it ran those first. And actually, if we check all of these, you can check whichever ones you want to run. And if you don't want it to change, then you can, for instance, I mean, here we calculate, or we have a gamma ray, so we could have used the log to calculate the gamma ray, but on the other hand, we can use the simulator to do it too. Yeah, and that's about it for that. Okay, so what we're going to do now is we're going to make a new log, and you guys can follow along. We're going to do the exercise that is let's have it open.
Bruce.
Yeah.
I'm sorry, but I don't think I really understood the difference of applying that box of nuclear run the simulation first or not that you have just explained it. Could you repeat it, please?
So if you have this checked, you recall the in the Petrophysical Calculator, we have the bulk nuclear properties calculation. And this runs, for instance, SNUPAR UT-NUPRO on the Earth model, right? And so for all the layers in the Earth model, it'll calculate thorium, uranium, potassium, bulk density, photoelectric effect, hydrogen index, neutron porosity, neutron capture.
And that is based directly in the composition that you have in that layer. So the difference, in other words, well, some other way I would explain it is, if you do that, you're running the simulation based on composition. If you don't have it checked, you're doing it directly on the property. Now that Bruce is going to show an example, it's going to be a little more clear. But it's whether you, it used to be a two-step process. Always, if you were relying on the composition would calculate, for example, gamma ray, and then gamma ray would be the input to run the simulation. But in many cases, you want to work with in the composition, not directly with gamma ray. So in that case, you keep that checkbox checked.
Okay, I think now I understood. Thank you.
I think, I mean, I guess another way of putting it is if you, there may be cases where you'll manually set the values for some reason or another. You know, maybe you got the, you know, I don't know, you're copying it, or you have some log that has the value and you want to, yeah, in the case of gamma ray, if for instance, if I use the log populate log for gamma ray, it would create a gamma ray value, which would in turn create uranium, potassium, and thorium values in the Earth model based upon that log. But then, so it had nothing to do with the SNUPAR or UT-NUPRO. Basically, you just told it exactly what the value at each layer is for the relevant Earth model properties, and then and so then it uses those properties to run the because what the simulation does is it figures out what the environmental effects will be like, what the layer effects, what the, you know, basically the sensitivity. It has sensitivity functions that figure out how different layers and different invasion zones are going to interact to give you a realistic log. But the actual values in each of those zones and in each of those layers come from the Earth model. And so this just says, this helps to determine how that those Earth model values are going to be calculated. And then from those, that distribution of values in the Earth model, it will simulate what the log response would be to those values.
Thank you. Okay.
Yeah, and so if you set it manually, you just uncheck that. But if you leave this here, then it will use whatever you have. And we'll see probably, I think, see some examples of the difference of that later. We might even be able to try that at the bottom of this. Actually, this one I don't think this. No, yeah, just set some values. So what we're going to do now is open up this resistivity anisotropy. You guys should all have that, and we're going to start with a new well and just follow the instructions here. And so the first thing we're going to do is set reference track limits from 0 to 150. And then we'll set the modeling limits from 20 to 120. We want to set the viewing limits, the reference track limits. Okay, there we go.
So reference track limits and then viewing limits. Okay.
Okay, so now start off there, and then we want to add 4 boundaries in order to have 5 layers. So we set them about every 20 meters or 20 feet here. I guess. Yeah, I say 20 meters, but the reason this is set feet because the global units were changed because of the first log that I imported was in feet. So
Yeah. Why don't you show them how they could change the units if they wanted to?
yeah, sure. Okay, so if we want to change the units here, we can actually go in here and change this to meters. And in that case, I'm going to, and I can also show you then how to delete a lot of layers at a time. So if we click the cross button, we can delete the layers I just made. And then we can go right there and do this again with the feet. Or with the meters, I mean. Okay. So now this is set at 20. All right, now I'll put the layers back in. And they don't have to be exact, but okay, and then we're going to use the table. Actually, the table is going to work better if we put a layer at the top, because otherwise I think it's going to give us, now let me look and see. I think if I recall, oh, maybe it will. Oh, I guess it works. Okay. Okay, so now in here, it's a good example of how to, we can set up a custom table. And what we want to set are the values that are shown in the picture there. So the first one is total porosity. Shale concentration. Oh, porosity.
So we're replicating the table that we have there.
Yeah, we're going to replicate this table. So we're going to use the table to set the layers as shown down here.
And it's set property group custom. Yeah.
And let's see, shale, porosity. Shale. What's the other porosity over here? Oh, matrix. Okay.
So,
I should have written them down here.
yeah, third and fourth are difficult to get.
What's that?
Shale porosity and matrix porosity, right? Yeah.
Yeah. Yeah. Unfortunately, I didn't notice that they didn't show up in the table, so I should have put them in the instructions. But anyway, so this one you can see the S, but the next one you can't see that it's the matrix porosity.
Yeah.
And then water saturation and shale structure. this a little bit smaller.
And shale structure, okay.
Okay, so we have velocity all 20. And note that you can use copy and paste in these.
So all of them have 0.2 porosity, right?
Yeah.
0.2 porosity. And all of them have 30% shale or 0.3 shale.
Right.
Now the matrix porosity, you may not want to input because it's constrained by all the others, and it has some numbers that are not so easy to punch in. But if you do the M4 structure, they're going to be updated. So really, the shale structure is probably the most important part that you need to. Everything needs to get to be set up right, but the matrix porosity is going to depend on the shale structure. The one exception are the last two because they are laminar dispersed, and those two are gonna, they give some room for interpretation for the matrix porosity. So make sure that your input, it's a 0.3, is that right, Bruce? 0.3 and 0.42.
Yeah.
The last two for matrix porosity, 0.3 and 0.42.
Yeah. Actually, maybe I can set. I should set this to enforced first. Okay. I think I did this before we had the enforced thing.
Yeah, that might be, but it makes it easier. So you just calculate and go back to the table, and it's got the right number. Oh, yeah, just calculate in the other one. And well, yeah, laminar dispersed, you should actually set them. The last two you actually need to set. If you go to Petrophysical Calculation and just hit calculate, because if you open the enforced structure, you can show them what is being enforced, and it's saying no, just on top of SNUPAR.
Ah, okay.
In the Petrophysical Calculator, yeah, there it's saying that it's going to enforce stone-stiver structure, and by default the order keeps the matrix porosity as the last variable to enforce, which means that is the most dependent variable. So it's the only one that is going to be modified.
Right.
And if you go, now that you hit calculate, you see the table, they are in the right value except those last two, because they're not aligned, so they're not constraining it that much. You will have to set that up explicitly.
Okay. So let's see. So this matches everything. All right, so when you have this table set up, then we use the Petrophysical Calculator to calculate the nuclear properties.
Also, water saturation.
Oh, I hit the wrong water saturation. This is irreducible.
No, you were right. It's I see. Oh yeah, you put irreducible.
Irreducible, interconnected. Six. That seems like a lot.
Yeah, no, you just need to use total. Total is fine for that one. Water saturation total or interconnected, that's also fine.
So quick question here, at the matrix porosity, you just put it 50%? Is that?
So the matrix porosity, the top one is 0.5. The second and third one have more complicated numbers, is 0.2857 and then 0.2429. But those can be calculated in the Petrophysical calculator, because if you have a dispersed or a laminar structure and you have set up total porosity and shale concentration and shale matrix, and shale porosity, that fixes the matrix porosity. You can go to the Petrophysical calculator like Bruce did, and that operation that we have that says M4 structure, no, in the Petrophysical calculator. What?
Oh,
Yeah, that M4 structure will make that matrix porosity be in the right number, be petrophysically consistent with the shale structure that you're saying that layer has.
okay. Then we want to calculate the resistivities and water saturation. And uncheck this. Check Archie's resistivity from water calculation.
Now, the equation that is being used here is what we have by default. And if you want to see what it is, you just go into that button that has the RC, stands for rock class. And in default, we have Juhas. So if you want to.
What these are, you can see the equations here and more advanced equations. Oops.
So if we want to, because all the layers that we have are in default, and so we may want to change the model here because it says we should use Archie.
Well, it says Archie's and similar. Does it say Archie's explicit?
Oh, okay.
I think we're not. I think we can't use it because we have shale. I mean, we're not going to see.
Yeah, in print, it's not a very good approximation. That's true. Juhas is better.
Archie's assumes a clean formation.
Right.
All right. So now, if we look at our well, and we plot the resistivities. Oh, stashed. Okay, so then when we plot the resistivities, you can see that the layer that is doesn't have any shale, there's no difference between the vertical and horizontal. And then
So it does have shale, it's just not laminar at all. It's just completely dispersed. The other ones have some level of lamination.
all right, okay. Yeah. Yeah, so this shows that the lamination causes a variation in the an anisotropy in the shale or in the resistivity.
Exactly.
And then I think, let's see, did we, just while we're at it here, I want to see if we have any interesting gamma ray values. Oh, we just have not much.
As yeah, gamma ray is just reflecting the shale porosity. So that's why we only have like the top ones have a value and the bottom ones have a different value.
So water saturation is.
Yeah.
Okay.
Constant water saturation, right?
So we're not going to see much effect here as far as the NMR. Well, I guess we would see.
O Pilates me manda mensagem dizendo que o professor não vai poder dar aula amanhã, tá num curso, não sei o quê, pediu para ver se podia ser hoje às 6 horas.
Let me.
Meio assim. Aí a coluna hoje deu uma doidinha.
Sorry. Mute. So next it was we wanted to show them how they can use the numerical plot.
Oh, yeah. Yeah, so if you insert a new track here and wanted to show for some reason, whenever I move one of these windows outside of this window, it makes all my windows close, which is really annoying. Yeah, so we can plot the shale fraction or some other value here. Actually, it's a little bit smaller. And put a numerical. And so this is handy sometimes. In this case, we put or shale concentration. I mean, this shows you the slight difference in the gamma ray. Or I think what I show in the example is that we show the shale concentration just to show that it's always the same. And yeah, the only problem with this is if you want it to be centered on this layer, you have to put another layer above it because it puts these in the center of the layers. So so for the top layer, it's a little bit confusing.
Well, you can add it. It's okay.
And then the other thing I could probably show, let's see if it makes a difference here. What happens if I calculate gamma ray log?
You're trying to show the
I was going to show the effect of the nuclear calculator if this works.
right. Yeah.
So now I simulated the gamma ray. And same size. Top. Okay, so there we can see, if you bigger. There we can see the simulated gamma ray now. And if I manually change the gamma ray in a couple of these, and then run this again, if I uncheck this because I manually did those, then you see that it matches the changes that I made. But if I set the nuclear calculation, run the nuclear calculation first, then it resets them to what the nuclear calculator calculates based on our shale concentration.
Nice.
So Bruce and Joaquin, I have a question here. If you go back to your calculator, your table of values, it's yeah, here. So I'm kind of confused why you have a matrix porosity higher than the total porosity.
So you can see that if you go here. So for instance, total porosity 0.5. So really any of these, that's sort of the advantage of the Thomas-Steiber diagram. It kind of makes all that very evident, because you can see here that the total porosity, in this case, the matrix porosity is where this yellow dot is, and the total porosity for the laminar case, at least, is clearly has to be below, because it has to be on this line. So the highest it can be is the matrix porosity. But if you, as you increase the shale concentration, it's only going to get smaller.
So I've seen that different porosities name different things. So we have to be very clear about what we mean by matrix porosity. Here in UTAPWeLS, what we mean by matrix porosity is the porosity left by the grains, let's say. So we assume in a dispersed system, like in a dispersed system, let's start with that and then we'll move to others. We assume that there are certain grains that are the matrix. I've seen the matrix word used for defining other parts, but that's what we use here. And then among those grains, there's a porosity, and in a dispersed case, that porosity can be filled up with shale in part. So that's going to reduce the total porosity, because a part of that porosity is filled up with shale. That's why in one way. And then if it's laminated, similarly, it can be well, it's going to be a combination. If it's laminated, you're going to have very thin layers of completely clean matrix and completely clean shale. So if the shale porosity is smaller than the matrix porosity, it's going to be smaller, and it could be reversed if the opposite. And then if you were in a completely structural case, what we mean is that you have a matrix that is in principle completely made out of the matrix, but it's been so long that some of that matrix turned into shale. So the shale that is added in a structural case is not filling up the porosity, but is taking over some of the matrix. And we don't have images for that. That might be a nice addition to make this a little more clear. But that is why. Does that make sense, Hesham?
I'm still thinking always total porosity should be the highest porosity that you have.
Yeah. So maybe
regardless of the nomenclature, total is a total.
total. That is absolutely true.
So the thing is, in this case, the reason that the total is smaller is because the total is literally the total. The total is the actual porosity. The matrix porosity is unfortunately not really a porosity. It is the amount of space that is not the matrix, or the sand, as some people would call it. And so as you add shale, it's saying the shale would go into the space between dispersed or laminar. The shale goes, I mean, it's even more clear with laminar, because in this case you have the sand and then you have layers of shale in between. And so if the sand, in this case, if the sand has a higher porosity than the shale, the more shale you add, the lower the total porosity, even though you haven't changed the porosity of the sand, but the total porosity has to go down. So what this is saying is, in this case, it's a laminar case, right? So that means we have alternating sand and shale layers, and the porosity of the sand layer is not changing, right? If you add more shale, you're just making the thin shale layers in between the sand layers thicker. And so, you're going from there being, almost, very thin layers in a layer of sand to mostly shale. And obviously, since the shale here has a smaller porosity than the sand, if you go to a pure shale layer, it's going to have less porosity than a pure sand. And as you said, the total porosity is just the total amount of fluid-filled space.
I'm going to share a screen. I made a real quick drawing. So it's I made with paint. Imagine this is a matrix with some grains. Of course, not realistic, but imagine that's it. And then you fill some of it with shale, and it's this part. So the total porosity is going to be smaller in this case compared to this case. The porosity of this is what we were saying, it's the matrix porosity. So it's larger than the total porosity, because the total porosity is taking into account that some of the space between the matrix, the grains that form the matrix, has been taken by some solid shale. And then,
I mean, I agree with you. I never liked that definition, but it's it's unfortunately the standard in the industry.
you can share now, Bruce. Sorry.
Okay, well, that was actually the end, so we're cutting
Okay.
the break.
Nothing else about. Okay.
So also a quick question here. So the Thomas Steiber curve is basically has at least three anchor. One is clean sand porosity, one is shale porosity, and one is like dispersed sand, dispersed shale sand porosity, if I say. So so in the first point, when you have total porosity, when the shale concentration is 0, so I believe that this total porosity has to be clean sand porosity or your matrix porosity. That I was just confused about that.
That's exactly right.
The first point in the when the shale concentration is 0, right? So you have total porosity is like 25%. So I assume that here your matrix porosity should be the same as here, as like 23 as you have here, right?
Yeah, that is completely right. Yeah, if there is no shale, the matrix porosity and the total porosity would be exactly the same.
So that's if I move this black dot over all the way to the right, then you see that they match, right? Because it's right on the yellow dot, which is the matrix porosity. I really hate this particular. Yeah, so yeah, clearly if the shale porosity, I mean, because right now we're constrained to this blue line. And clearly if we total porosity last. We're constrained to this blue line, and so if we bring it all the way to the left, then total porosity equals the matrix porosity, and to the right it equals the shale porosity because it means 100% shale, and in between it's just the combination.
Yeah, and in the results you saw that even though we have the same shale concentration and the same total porosity, the anisotropy makes the resistivity look different in each of those cases. I don't know if you want to elaborate a little more in the nuclear tools, but, or you want to take a break and come back.
We're going to be doing more nuclear later on. I think, I don't know if there's much more we can, I mean, we showed that, I don't know, did you guys see the effect of that you were asking about before with the what effect that checkbox has? And then this checkbox here, I'm trying to find my here. So when we looked at the gamma ray calculation, if we manually move close the, so if we manually moved these gamma ray values, then, and we uncheck this and run it, that means that it will not run the nuclear calculation first. And so it's just going to take whatever values are currently set in the Earth model. And so then you see that the simulation then matches those the Earth model values. But if we say run the nuclear calculation first, then it goes, oh, well, we've played around with the values different than they were because we've been playing around with that layer value. But basically it goes back to whatever is the nuclear calculator calculates, because it ran that first. So the ones that we didn't change went back to their old values.
Very good. And anybody has questions or want to share something?
Another quick question about this Thomas Stever graph here. Are you going also to show the net to gross value here, or at least I don't see that? Maybe you show it somewhere, I don't know.
No, we don't have it here.
Yeah, maybe it's good to have also the net to gross value.
Yeah, that's a good idea, actually.
Which graphs are those?
Net to gross.
Netty?
Yeah, net to gross in Thomas Stever graph, yeah.
Yeah, we can. Yeah, that's a relatively simple addition we can do.
I thought it was on there. Well,
What is
I thought you called it something else though. I thought you called it a shale fraction. I thought it was on there. Somewhere.
We couldn't catch what you were saying very well.
Sorry. Is that better now?
Maybe.
Is that any better?
Yeah, that is better.
Yeah, I thought it was on there somewhere. I thought I'd seen it somewhere, that there was a sand count, but you don't call it that. You call it something else. Sorry, I thought I'd seen it somewhere in there.
Yeah. Well, we have I think we have the inverse, not the inverse, 1 minus. We have.
Is it a lamination factor you call it? Is that not what you call it?
No.
No,
lamination
okay.
factor is the, well, it's just, it only matters for laminated dispersed and laminated laminar structural cases, and it's just how close is it to laminated. But I think the net to gross that you're talking about, it would be just one, hydrocarbon saturation minus residual. Is that right?
Okay, I think I'm getting confused now. I mean, I thought when, sorry, I didn't catch his name. Fahi, was it? I thought he was referring to, I've seen it called a sand count. So it's so in a shale sand lamination, the ratio of the sand to shale, I've seen it called a shale count, a sand count, or I've seen different names for it.
I see. But
Yeah, maybe
Was it-
the
and-
lamination factor is just the same as that one, because basically is that you have the thickness of the shell to the total thickness, right? So maybe the lamination factor is actually the net to grass.
Yeah, that's what I was thinking. That's
Yeah.
what I thought when I saw it anyway. Yeah.
Yeah, well, but net to grass is more popular name for that rather than this
Okay.
lamination factor.
Yeah.
I don't know if it's the same, but this represents how, I mean, this is exactly what fraction of the shale concentration is laminated.
yeah, if anything, I think it would be 1 minus that.
And actually, you can go here and it shows what these values are.
Yeah. Well, we'll look into it and make sure we put it there. All right. Any other questions or comments regarding these or nuclear simulations? If not, then let's take a 10-minute break and we come back for resistivity simulations and inversion. So we come back at 2:25. All right. So see you in a bit.
Okay. Yep.